of talks devoted to an interesting field, as last time, searching of galactic axions and superconducting quantum devices. Today is the third talk, and I would like to introduce our speaker, Professor Woohyun Chung, a research fellow at Center for Axion and Precision Physics Research, Institute of Basic Science. Professor Chung has got his PhD in 1995 from University of Pittsburgh, USA, and after that kept various research positions at the University of Wisconsin-Madison. Dr. Chung, main areas of expertise, experiments in high-energy physics and muon detectors. Currently, he is overseeing the axions experiments on CAPP, Center for Axion and Precision Physics Research. I would like to give a floor to Professor Chung for a talk on accelerated axion search at CAPP in Korea.
Thank you very much. Good afternoon, everybody. It's my pleasure to be in this PCS seminar. I really like to talk about the experiment at CAPP. So my main title is a little bit misleading, but that's my main focus, actually, trying to speed up the axion search experiment, because we established for last 7 years, we established the axion experiment in Korea, and now we have many refrigerators and many magnets, but my main concern is it'll take forever to search the whole vast area of a possible axion mass range. So I like to talk about actually the third part, all those improvements we are trying to make in through R&D. In the introduction, I'll go through very quickly about dark matter axion and also the haloscope, CAPP-PACE haloscope, and the mechanism to detect the axion in the microwave cavity experiment. And in the second part, I like to introduce what we are doing at CAPP. We call that collectively cool task experiment, CAPP's ultra low temperature axion search in Korea. And we took some data for the last 2 years. So I'll talk about a little bit about the our physics data. But still, my main focus will be on the third part, all those R&Ds that we're doing. So this is sort of obligatory, the introduction of axion search. The axion, as you know, is from trying to resolve the strong CP problem in standard model. And Patrick Quinn, 1977, came up with a very elegant solution by adding a global symmetry to resolve it. And evidently, there should be a particle, it's called the axion, named by Wilczek, named after a famous detergent brand. But still, axion sounds very good to me. The axion is getting more and more popular these days, and getting a lot of people are interested in looking for it. The axion is a Goldstone boson, a pseudo Goldstone boson, and is a very small mass. The mass range is 1 micro eV to 10 MEB, and it's extremely weakly interacting. And the local halo density is 0.45 giga-electron volt per cubic centimeters. That means it's everywhere. The velocity is 10 to the minus 3. So it's moving together with us. That means if we look at it, the Q factor of the axion will be 10 to the minus 6, about 1 million. So there are many ways, people come up with many different ways of searching for axions, but the first one and the most popular one is by Sikivi in 1983. It's called haloscopy. It's using basically microwave cavity submerged into 2 photons and looking for the access through the RF chain. So if you look at it, this is the way to categorize all those different axions is cosmic axion, solar axion search, and also the laboratory man-made axion search. But all in all, the most sensitive one is the microwave cavity axion search. So if you look at when axion converts to 2 photons, the conversion power is excluding all those constants. It's basically proportional to the square of the magnetic field and the effective volume, and also the Q factor of the microwave cavity. So the present technology, the power we're going to detect is about 10 to the minus 22 or 24. So it's a level of yoctowatt, which is very, very small. And when we're looking at the noise over the signal to noise ratio, you can also, maybe I can you see the pointer?
Yes.
Okay. So this is a conversion power and divided by the temperature of the system. So the noise is usually dominated by the temperature. It's either physical temperature or the noise temperature from most noise is from the amplifiers actually. So the signal to noise, if you look at the signal to noise ratio, that if you like to increase the signal to noise ratio, you have to integrate for a long time. So actually the figure of merit in this axion detection, microwave axion detection, it's a scan rate. So how fast you can scan. So the DFDT is this. So if you can look at it, maybe I can throw some cartoon. This is Sikivi's haloscope. So basically, axion converts inside the microwave cavity, submerged by the very strong magnetic field. So axion goes, the photon comes out it happens to be the same. The photon's frequency is the same as axion mass in this case. So if you basically like to detect photon as an excess in this RF chain. So basically you like, in this scheme, you like to put everything into a very noiseless environment, which is very low noise, a very low temperature environment. So we need cryogenics. And also, like I said before, our noise is dominated by amplifiers. So we like to have very low noise amplifiers. And also, these two are suppressing your noise. But also, we like to boost our signal by using very powerful magnet. And also, I also mentioned that the volume really matters. So we like to have as much volume as possible. So we need the very powerful magnet with a big bore. So one of the things we like to have is 25 Tesla magnet, which doesn't exist yet. And also we like to have 12 Tesla, which is not very powerful, but it has a very big bore, like 32 centimeters in this case. So other than these two, we also like to have the photon actually in the first stage was multiplied by, amplified. The photon signal gets amplified by microwave cavity. So we like to have as much as high Q as possible. So usually the Axion search people usually use copper or copper plated cavity. But I remember 3 weeks ago, Claudio Gatti talked about superconducting cavity that they make. We also tried superconducting cavity. So that our R&D really includes big bore, powerful magnet, also superconducting cavity, and low noise quantum amplifiers. And on top of that, I didn't have it here, but we also like to have the multi-cavity to explore the high frequency, high mass region. So the haloscope is the most known sensitive method, but still the possible mass range is huge. So present technology, if you like to scan through the whole range, it sort of requires many refrigerators, many different magnets, and maybe in the higher region, probably we need the multiple cavity. And all those, we need all those innovations and breakthroughs to speed it up. From my calculation, present technology will take 100 years to scan all the possible axion mass range. But we like to take advantage of the advancement of superconducting technology. It's also superconducting magnet technology, and also the quantum amplifiers like JPA or traveling wave JPA, and also superconducting cavity. So at CAPP, I categorize 3 different R&Ds. So we like to maximize signal by boosting B square V and Q. So we already have 12 Tesla, 32 centimeter bore. It's not HTS, it's LTS, niobium tin magnet. We have that this year. And also right now they are installing the magnet power supply right now. So we're gonna use it at the end of this year or very early next year. So the time that we're gonna save by doing it, having this magnet is about 100 times over the normal small cavity 8 Tesla experiment. And the superconducting cavity, I call that YBCO cavity in our case, is going to, it's not a square of the volume, but we can speed up like 10 to 20 times faster. I'm going to explain that in the coming pages. And another second category is to minimize noise. So physical temperature, we already achieved the coldest experiment in the world. Our cavity temperature is below 40 milli-K right now. And our amplifier, we started using the JPA quantum amplifier this year, and it looks very nice. So I'll talk about that. So by doing this, we're gonna improve it more than an order of magnitude. Actually, from my calculation, it will be 50 times faster by doing this. So in order to achieve that, I guess we have to optimize our cryo RF receiver chain. And we are also thinking about having a single photon detector sometime, not right now, but we are thinking about it. And in order to, suppose you have those two, achieve the maximize signal, minimize noise, still, in order to scan higher frequencies without shrinking volume, you need something to do it. In our case, we already developed a multi-cavity by Woohyun. So he called it pizza cavity. It looks like pizza. But this example here, is showing that the 6-cell cavity. So usually in one of our dilution refrigerators, its frequency is about 2 gigahertz. And this 6-cell cavity frequency is around, center frequency is around 6 gigahertz. And also we are doing dielectric rings, but I'm not going to talk about this today. Oops. Okay. So this is briefly showing that what we did the last 7 years. Our center was founded in 2013, but we haven't got anything until 2016. So I remember 2016 in February, we had our two of our first dilution refrigerators. It's called BF3 and BF4. And then later, 2017, we had 2 more. So right now we have 4 Blue Force dilution refrigerators. And also we put it into a low vibration area we developed 2016. So in Munji campus of KAIST, in our building, we modified it. And right now we have 7 low vibration pads. And 2 of our dilution refrigerators is on it, and also our 12 Tesla Leiden refrigerator is also on the low vibration pad right now. So we established the multiple axion experiment until 2019, and this is the picture I had in 2020, this year. We were running 3 different experiments, actually CAPP-PACE, CAPP-ATB, and CAPP-90. MC means multi-cavity. And this CAPP-12TB is our most powerful refrigerator, and also powerful, the combination of powerful refrigerator plus powerful magnet. So this one, it will be in commission starting this year. So if I show more detail, right now we have 7 refrigerators and 5 magnets. And those 2 dilution refrigerators, we are using it to test our quantum amplifiers right now. So once it's done, and probably next year, we will get 2 more 12 Tesla magnets. But these are not the big bore magnets, a 10 centimeter magnet. So then we'll have whole array. We could have basically 7 different axion experiments. So this is the organization of our axion research at CAPP. We call that the cool task. Right now, we are taking data with 3 experiments: CAPP-PACE, CAPP-ATB, and CAPP-MC. And CAPP-12TB will be in commission this year. So these are some parameters that our physics data. I'll show a little more detail later, but we started taking data with this CAPP-PACE starting 2018, collecting commissioning data, and then CAPP-ATB was running with 4 times KSVZ level, and CAPP-MC multi-cavity is a proof of concept thing with the 2-cell cavity, and CAPP-12TB is still in. So right now we are using CAPP-PACE as a sort of guinea pig. It's using JPA right now, and we sort of completed our first run with our JPA. So this is the axion landscape with before CAPP came into this game, and the CAPP-PACE. In 2018, we collected 10 KSVZ data in this area, which is about 2.5 gigahertz range. So before, you could see that there's something missing in between in this range. So we were trying, we're trying to fill it up with the 10 KSVZ level. And also, if you can see it closely, there is a tiny, tiny thing almost touching KSVZ level. This is only 1 megahertz span. So in order to do that, without a JPA, it took us about 2 months to run. So after we completed that at the end of 2018, we said, this will take forever. So that's one of the reasons why we developed JPA. So this is another refrigerator. This is a little bigger magnet with the bigger volume. Volume for this one is about a little less than 4 liters. And base temperature, the cavity temperature is about the same as PACE, below 50 millik. I think they took data with about 40 millik. And they used the Hempty amplifier of noise temperature of that was around 1K. And this we published in PRL this year. And also we took the data with not so, this data was from the helium-3 refrigerator. So this one, we like to prove that our new concept of multi-cavity, this one, the two cells cavity works. So this is our first result with the multi-cell cavity covering about 4 gigahertz range. So, and also this year, we took data with the JPA. So our JPA worked beautifully, and we took the data of 30 megahertz scan in 1 week. So which is, well, it says 2K SVZ level, but it's about 36 times faster than our previous experiment. So naturally, I have to talk about the JPA development in our R&D projects. We are collaborating with Nakamura's group of University of Tokyo in Japan, also RIKEN. So they provided us about 200 chips in 3 different batches, and the range of their chips from 1 gigahertz to 6 gigahertz. So after we got them, we packaged them ourselves, and we'll make shielding ourselves, and then we tested it and characterized it in our using our 2 dilution refrigerators. So these chips, these JPAs are rather narrow bandwidth JPA. The bandwidth is about kilohertz range, but we can use the flux coil to change the frequency about 30 megahertz. But it has it is a very simple design, but it has excellent noise temperature. So very so close to the standard quantum limit. So like I said, we completed taking data around 2.3 gigahertz of scanning about 30 megahertz range. And we also like to another test. We tested 6 gigahertz JPAs, and they look very nice. So we like to take data with the 5.5 to 6 gigahertz using pizza cavity, the division of 6 cells and 8 cells. So also we have the traveling wave JPAs, which have a huge bandwidth from INFN. Gotti gave us that's traveling wave JPA. So and also we got another traveling wave JPA from Manchester. Professor Pashkin provided. So we are testing both of them right now. So if you look at some of the characteristics of our JPA, we sort of completed our first papers, I think we're gonna submit it next week. So this JPA the result was testing 6 gigahertz and 2.3 gigahertz. And this is around 6 gigahertz, 5.9 to 1. And this is the trying to optimize and find the lowest, the point where, which gives the lowest noise temperature area. We sort of made this kind of map, and this is sort of a histogram of collecting all the noise temperatures. In all those cells, we measured the noise temperature, and this is the result. The lowest one for this 6 gigahertz JPA was around 150. So which is, close to the standard quantum limit. So another JPA we tested was 2.3 gigahertz JPA. It didn't go to the standard quantum limit yet, but it was pretty good enough actually for us. And if you read it, this is very small, but our noise temperature was around 120, 130 milli-K. So, which is, very nice. So we put it in our Axion experiment. So we take the HEMT out and install our JPA. You can take a look at here. This is a JPA shielding. Later we put it upside down, but this was initial picture. So we took the data with it, and our combined system noise temperature was little less than 200 milli-K, which is the lowest noise temperature in any Axion experiment. So in this, it depends on the frequencies, but nobody had that this kind of low noise. And our physical temperature was around 50, but adding quantum limit is 72 milli-K, and our JPA added noise was 120. So this one compared to our first commissioning data, because we used exactly the same setup, except we replaced our first preamp with the JPA. It's 36 times faster scan. So this one shows the about 30 megahertz range scan up to a little over 2 KSBZ level. So changing gears, I'd like to talk about our YBCO cavities. When I started this, 2 years ago, I looked all over and I didn't see any papers about superconducting resonant cavity for last 15 years. And, but we really like to improve our conversion power more than 20 times. It's worth it. So we got help from KAIST. There was a superconductor expert, Professor Yum. So he worked with us to, first we have to find the right material. Niobium doesn't work. Niobium Ti, it works in the low field, but up to 8 Tesla, probably not. So we used the sort of YBCO style, HTS, high temperature superconductor. We call that RAPCO, rare earth BCO tapes. We first fabricated our first superconducting cavity last year, actually, in a small version of 6.9 gigahertz. And as we expect, it holds the and show very high Q factor up to 8 Tesla. So we're gonna publish it, and I like to show a little more detail about that. The natural choice, we have to use type 2 superconductors, otherwise it doesn't work. So between all type 2 superconductors, our best choice, you can see that YBCO, because it has second critical temperature is very high, like 100 Tesla. So we can use it. So this one is perfect for us. And also it has a very high depending frequency. Depending frequency of YBCO is about 100 Tesla, 100 gigahertz, I'm sorry. And if you look at, this is very old paper, but if you look at it, copper is right there. And this one, even in a small field, it's with 90 degrees means it's tangential, it stays. So we picked the YBCO naturally, but it has a big problem, which is YBCO has texture. It's biaxially textured. So if you have different angle, it doesn't work as well as the 90-degree angle. So the grain has to be aligned with our magnets. So in three-dimensional microwave cavity, it doesn't work. So the sputtering YBCO into a concave microwave cavity doesn't work, and nobody wants to do that. So naturally, we look for the best made YBCO tapes. So those are the tapes that was used for making HTS magnets. So the only problem is they usually it's a tape, a very narrow, like 1 centimeter tape. So how we gonna do it? Even though YBCO is perfect material for us, we have to think about how to attach those tapes onto the cavity inner surface. So our solution was, to me, it was easy because the main mode that we're using for the resonance is the eigen mode is a TM010. So in this simulation, you can see that all the electrical line is it's aligned with through the surface. And what this one tells you is when you split the cavity vertically, it doesn't have any effect on your Q factor. So we actually use a vertically split cavity for our normal Axion experiment, but this one, because of the tape size, we have to cut it many more pieces. So this is, I call that melon cavity because I gave the melon cut. So if you look at the picture, each pieces, we put the YBCO tapes like this, and the YBCO surface is exposed in this cavity, and then put it together and measure. So this is the result. Actually, this is a second try. First try, the Q factor went up to 150. Our surface was miserable, so we put the second try with a better surface, and our Q factor went up to 300, more than 300,000. So, but the amazing thing is, you can see that here a phase transition, and also it goes up and up. The real test is when you put it into a magnetic field of up to 8 Tesla, and it jumps up and then stay. So that means we can use it up to 8 Tesla. So if you look at the previous picture again, it has many gaps actually between tapes. So that's probably because we couldn't reach the million of Q factor because of those gaps. So we like to improve it and trying to minimize those gaps. So this is our new generation superconducting cavity. This is a design that minimize non-superconducting gaps as much as possible. And so we are doing that. And I think we're gonna have the measurement probably in November. End of November, I guess. And also, we are doing niobium tin sputtering too, because we think niobium tin is still a very good material for many odd areas. So we fabricated the niobium sputtering machine, niobium tin sputtering machine. It's kind of hard to sputter it and then translate to annealing chamber, and annealing chamber also has to be very high temperature. So it took us about more than 6 months to complete it, and it's almost done. And so we're gonna do the first test probably next week. So all in all, our superconducting cavity R&D is going very well and promising. So this was the plot I showed before, the before CAPP's data. So these are the CAPP-PACE data we added last 2 years. And but when you combine all those weapons that we have developed through R&D, huge, a very powerful magnet with a very powerful refrigerator in 12 TeV, plus quantum amplifiers, plus the superconducting cavity, plus multi-cavity. We like to search through all this region by 2025. So in all in all, these are the naive calculation of those the improvements we can get through this R&D. So it's a multi you have to multiply all of them if you achieve all of them. So in summary, CAPP has excuse me, successfully established multiple haloscope axion documentary experiments in Korea. And so we, I think I forgot to take this one out. We completed the first run with the quantum amplifiers, but we like to really do it with the quantum amplifiers plus superconducting cavity very soon. And major improvements, the major expectation is on CAPP-12TB in coming years. And R&D on JPA and superconducting cavity looks very promising. So you should stay tuned. Thank you very much.
So thank you for your talk. Let's all thank our speaker for this talk. And the floor is open for questions. So from the audience, if you have any questions, you can either use
my name is Evgeny Lichev. I have questions. So can you talk a little bit in more detail of construction of your parametric amplifier? So I am interested in, this is bandwidth, this is traveling wave or not? Or which is bandwidth of your amplifier?
This is not traveling wave.
This is not traveling. Okay.
Right. The bandwidth is order of kilohertz range. So
this means that you use Josephson junction just to shift resonance frequency. So this is narrow band, and then you can simply scan. And what is the range of frequency you can scan?
We are testing third batch, and we have tested a second batch. I only can talk about the second batch.
Okay.
Second batch, the one we used for the Axion experiment, with one chip, we could scan 30 megahertz.
30 megahertz. Okay.
Right.
And for this second, this noise temperature 167 euro. This is this one or not? What is noise temperature?
Noise temperature of 6 gigahertz one. The lowest noise temperature we reached was 150K. Milli K. I'm sorry.
Okay. So thank you.
A question. How important is it to go beyond the standard quantum limit? As far as I understand, it is still quite a way until you reach the standard quantum limit. Is there any reason from your point of view to go beyond that?
We discussed that with the people from Nakamura's group, and looks to me that it's pretty hard in the first. We need more. We need actually 2 JPAs to achieve squeezing. You mean squeezing, right?
Not necessarily. Suppose squeezing is one possibility. Yes.
Right. So, but from their calculation, it doesn't look like we get we get more by doing that. So I think close to the standard limit is probably the limit we could reach. That's it.
Okay, thank you.
Okay, more comments, questions from the audience?
It's Claudio Gatti from Rome.
Yep, please go ahead.
Concerning this last point, can you comment, I don't know if you can, about also the recent measurement from Highstack with the squeezing? I mean, they claim they reduce the noise. So why do you say Nakamura is non-optimistic on this? I understand it's not easy.
Right. Maybe I'm not qualified to answer the question, but to me, the squeezing doesn't give you a whole lot of merit. Well, to me, I would go directly to single photon detectors. You can squeeze twice, actually. and gain, 2 times. But in order to do that, you have to have a real expert to do that, right?
Oh, that's for sure.
Right.
Yeah, I'm trying to read the paper. It's not yet clear how they did it and how it works actually.
Well, the haystack has the GIST guys working on it, including Ben Brubaker, who's in GIST right now. So they have plenty of experts. And for us, if we like to do that, we have to have all those people from Nakamura's group. So it's, we don't, in this COVID-19 situation, we don't like to do that for now.
And, with the Nakamura, are you planning to do the single photon? I mean, he already did this qubit coupled to the Higgs sphere inside a cavity.
Right. They are doing it right now, but the one of the things we are looking at right now, maybe I'm not qualified to say anything in detail, but we are, Nakamura's group's work is still away. Like I said, we don't have an expert, but we have at KAIST, we have Rydberg atom expert. So we like to try that first.
Okay, thank you.
Mm-hmm. Thank you.
Okay, thanks a lot, guys. Meng has a question. Please go ahead, Meng.
Yeah, so it's a very naive question since I'm not working on this axion field. I just wonder that if this axion is a dark matter, is that means this axion is in Bose-Einstein condensation in the universe, or can you make some comments about that?
That I'm not qualified to answer the question, I guess. Right. It's more of theorist region.
Yeah, I can comment. Maybe it was an Einstein condensate outside the galaxy, but inside the galaxy, it is not anymore. This is what I understood. I mean, kinetic terms, kinetic velocity, and it's not anymore Bose-Einstein condensate. So from our point of view, it doesn't really matter.
Right.
Okay. Okay. Thank you.
Okay. Any more questions, comments from the audience? Well, doesn't seem like. So then let us all thank our speaker once again for this wonderful talk. And with that, I would like to officially end the PCS seminar. So thank you all for joining in.
Thank you.
Thank you.